All right, so this is part two to section 5.5. We're still on the substitution rule, use substitution. So I wanted to go back and do an example where I picked the wrong u. So this is an example of picking the wrong u for use substitution. I'll show you what to look out for. So if this does happen to you, you can see that you've messed up and go back and try again. So that's brings up a point I want to make with these use substitutions. It's I can go through these and I can do these problems pretty easily. I know what to pick for use substitution because I've done this a bunch. The first a couple weeks that you're doing it, it's very likely that you'll make mistakes. So let's see what it looks like when somebody does make a mistake. So let's look back at, I think it was the first example I did for this section. We have integral x cubed cosine of x to the fourth plus 2 dx. So you remember when I did this one, I picked for my u the x to the fourth plus 2 because differentiating it gave me an x cubed, which appears here. Let's go ahead and pick the wrong u then. So let's say that I let u equal to so there are a couple. So let's do x cubed. That's gonna give me the easiest mistake here. So if let's say instead of picking x to the fourth plus 2, I picked x cubed. So if I do my du, then this is going to give me 3x squared dx. And I'm going to go ahead and solve for dx here. I'm going to get du over 3x squared. So now I'm going to plug this into the integral. So this is going to be equal to the integral. So x cubed is u. So I'm going to get u cosine of x to the fourth plus 2. And if I plug in for dx, I'm going to get du over 3x squared. So if I try and simplify this is what I'm going to get. I'm going to get 1/3 the integral u over x squared cosine of x to the fourth plus 2 dx. Du here. So now if you look at this, remember, if you go back and look at the correct way of doing this example, at this step, everything that was an x canceled out. Here I cannot do that. I still have an x here, and I have a function of x there. And so I can't, so because my integration variable now is u, I can't integrate these. And besides that, you would be really hard pressed to come up with an integral and any derivative for that. So this is what you want to watch out for. If after, I plug in for dx and I don't get all the x's to cancel out, then I've made a mistake and I need to go back and try something else. Or I need to look for, can I make another substitution that makes it work? In this case, no. So just be aware that, this is not what you want to do. This is a mistake here. Okay, so let me go on to the next example. So this one's going to seem pretty simple. It's an important one though. Let me switch back to black. It's important though because this type of integral is one that pops up the most. I've done this integral a million times, or one similar to it. So we have e to the 5x dx, this integral. And so actually, I think the good news for this one is no matter what, so as long as you pick u, that appears here in this e to the 5x, no matter what you pick, I think it's actually an okay u to do. I'm going to pick the one that, I would have thought off right off the bat. So I want to do this integral, and you might be able to do this in your head, and eventually you will be able to do it in your head, but now we're going to use u substitution. So I know the integral for e to the x. So I want this thing here to just, I want this 5x here to be just, a u or an x there. So what I'm going to do for this is I'm going to let u equal 5x. And even though, I don't have anything else appearing, that's going to be okay because in this case, du is 5 times dx. And now when I solve for dx here, I'm going to get dx is 5 divided by du. I'm going to plug into my integral. So this is going to be equal to the integral. 5x is now u, so this is going to become e to the u, and I plug in for dx, I'm going to get 5 divided by du. No, sorry, I've made a mistake here. Dx is du divided by 5. You shouldn't have these differentials in the denominator. It doesn't make a lot of sense. So this is du divided by 5. So that's my mistake. Okay, let's simplify this. So this is 1/5, the integral e to the u du. And again, I know how to integrate this one. The function I differentiate to get e to the u is going to be e to the u, plus my constant, of course. And now I want to go back and just make it in terms of x. So this is 1/5 e to the 5x plus c. And that's the end of the problem. So you can check, you can go through, take a derivative, you'll get the e to the 5x back. And again, you'll be able to, eventually, if you stick with this, you'll be able to do this pretty easily without having to do a u substitution. All right, so let's move on to the next example. So this is an example of making a second substitution, we'll call it. All right, so this example, so we have the integral of the square root 1 plus x squared, x to the 5th dx. So again, this isn't something that we just have in a table. We have to use a u substitution in this case. So if I look at this, I can, if you start thinking, so I always go through, do a couple, when I was doing this to begin with, I would go through, do a couple in my head, see if anything pops out. So if I let u equal x to the 5th, I'm gonna get 5x to the 4th, and that doesn't help me at all. If I let u equal 1 plus x squared, I'm gonna get 2x. And you can see that, that might not be, what I need right off the bat, but it seems like the best place to start. Seems better place to start than x to the 5th. So let's let u equal 1 plus x squared. So then du is equal to 2x dx. So let's see what happens now. So if I plug this all in, I'm going to get the integral square root of u x to the 5th dx. So I can go through and solve for dx. I've been doing that. Dx is then du over 2x. So if I plug in dx here, I'm going to get du over 2x. And if I clean this up, cancel the x's, pull out the factor of 1/2, I get 1/2 the integral square root of u, x's cancel, and I get x to the 4th du. Now this seems like a problem because I have an x and I have a u here. So if you remember with that last example, I don't want to have any x's at this point. But there's a trick for this one. So if I can figure out what x to the 4th is in terms of u, that might be, advantageous for this problem. So let's go ahead and figure out what that is. So if I look at let's do it on the side here. If I look at my relation, u is equal to 1 plus x squared, I can solve this for x squared pretty easily. I'm going to get x squared is equal to u minus 1. But I don't want x squared, I want x to the 4th. So if I square both sides, I get x to the 4th, so x squared squared is x to the 4th, is u minus 1 squared. And that puts me in a better position because now this is 1/2 sorry. 1/2 the integral square root of u. X to the 4th is u minus 1 squared du. Okay, so you look at this and you start thinking, okay, that didn't really seem to help much. I can't, think of an antiderivative of that off the top of my head. But if you look at what's happening here, this thing here is a polynomial. And you have the square root in front of that, but if I expand all this, I'll be able to write this in terms of powers of x. So let's continue. So I have to make a new page here. So 1/2 integral square root of u minus 1 squared du. So we have 1/2. Sorry. 1/2 the integral square root of u minus 1 squared du. I'm going to expand everything. Actually, I'm also going to, at the same time, rewrite this square root of u as u to the 1/2. U minus 1 squared is u squared minus 2u plus 1. And now if you look at this, you can see that, if I distribute this 1/2, I can, use my rules for exponents. And I'm going to get, so u to the 1/2 times u squared, that's going to be u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. Let me make that a little neater. And now this is something I can integrate. So I'm just going to go ahead and do it. So I have this 1/2 out front, and if I integrate all these, I'm going to get u to the 7/2 divided by 7/2 minus 2 u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2 plus a constant. Okay, so now let's simplify things. I'm going to go ahead and plug in for u again. So when I do that, I'm going to have 1/2, all these fractions on the bottom. So the 7/2, 5/2, and 3/2, you just flip those up. So this is going to be 2/7 times u was 1 plus x squared. And this is to the 7/2 minus 2, flip up the fraction, 2/5, 1 plus x squared to the 5/2 plus 2/3, 1 plus x squared to the 3/2 plus a constant. And going through and simplifying the rest of this, you're going to get 1/7, 1 plus x squared to the 7/2 minus 1/5, 2/5. So this 2 cancels with, so the 1/2 cancels one of the 2's, you're left with 2/5, 1 plus x squared to the 5/2 plus 2/3, 1/3. 1/3 because the 1/2 and the 2/3, you get the 2's to cancel. 1 plus x squared to the 3/2 plus your arbitrary integration constant. And this is an x squared here. All right, so that would be my answer here. So you'll notice that this one was a little more difficult than the others, or than the other ones we've done. And the reason being, let's take a look back at the first page. After I did the u substitution, I was still left with this x to the 4th in the integrand. So I'm talking about right here. Talking about right there. So after doing my integration, I still had that x to the 4th, and I had to go back and use my formula for u in order to figure out a formula for x to the 4th. that made things a little messier. There's no getting around it, and so that just, again, it just makes things more difficult. So those were my examples for this part. I'm going to stop here. Next section is going to be we're going to deal with definite integrals and talk about how to do U substitutions for those. So I'm going to stop this now.